Okay, hello and welcome to my channel. Today we're going to be talking about the 1D scattering problems. So in this system, our potential would look something like this, meaning that our v of x is 0 when our x is greater than the r. It is a potential when it is between 0 and r, and when x is less or equal to 0, that would be infinity, meaning that when it hits this part, it would bounce back. Whether it is the same function or not, we don't know. Okay, so now we're gonna split this into two cases. So our first case is when there are no potential. All right. So when you have no potential, your drawings or your plot is gonna look like this: a flat line on this side and infinite potential on this side. This is 0. Okay, and when you have something like this, remember your solution. Here for this no potential system, I would write my function as phi of x. So phi of x would equal to, well, ae ikx plus be minus ikx by continuity and boundary condition. Okay, so when you send your wave function in, that would be e minus ikx, and what you get back is e ikx. Okay, so with this zero potential here, what you would get from your Schrodinger equation is that, well, minus a is equal to b. From your conditions, I'm sorry. From your conditions, you would solve that, well, minus a is equal to b. So from here you can put this in as phi of x would be proportional to e of ikx minus e minus ikx. Okay, so it already looked a bit familiar here. This would give us the sine function, but we are missing the 2i. So we're gonna divide it by 2i. So when you divide it by 2i, you split it out and you would get two wave function at 2 points, at 2 region, I mean. That would be 1 of x and 2 of x. So I take the first one to be equal to e minus e minus ikx over 2i. The other one is e ikx over 2i. And you see the minus ikx is your incoming wave. So this guy is also phi in. This guy is phi out. So, all right. And your wave function here would be equal to something sine kx. All right. So that's it for your first case when there are no potential. Now let's move on to a case where there is potential, meaning that what bounced back would not be the same. Well, allegedly, since if you remember on the last video, what bounced back would be a phase, would just have a phase shift. So technically they're still the same, but with a different point of origin. So the second case, when with potential. Okay, so now your system will have this v of x, where there are something in the middle here, right? And your wave function, now I write as psi, would be e to the ikx plus 2I delta over 2I minus e minus ikx over 2I. And you see this part rule stays the same as when you send it in, it is the same thing, but when it bounced back, it would have a phase shift as shown here. Okay, so this you can write it as ei delta, you factor that out, a sine function of kx plus delta. Okay, so these two you can see are essentially the same thing, with the only different thing here is the phase. Okay, so what you want to do now is find its square amplitude. So we take both of these guys, psi of x, and we square them. What you get here is sine square kx. This is sine square kx plus delta. Okay. And if you don't remember, when you have something like this, it basically means that they have the same amplitude but different point of origin. So for example here, I have a graph of your phi of x here, okay, and I want to draw my psi of x. You would get that it would have the same amplitude, but it would be there would be a shift in the phase. So different point of origin, but essentially the same thing. This is psi of x. Okay, so from here you get that when your delta is greater or less than 0, as you remember, a plus is a shift towards the left. So when this is greater than 0, this is a shift to the left. And same here, to the right, right? Okay, so that is it. And from here, from these two cases, you can get that this guy and this guy basically equal to each other, but there would be something in between them. And that is what we call the scattered wave. So erase this part, erase this part. Okay, so these two are essential. Oh my gosh, out of ink. These two are technically the same with a different in phase, and that is where our next thing comes in, which is the scattered wave, which is a piece that is kind of out and that would vanish without a potential. So to calculate your scattered wave, you would take these two and minus them. Okay, and what you get, I believe, is something times a function of sine. No, it is something times. Yeah, it is something times a function of sine. Just believe it is something like this. I believe. No, this is purely of delta as a sine delta, and people are gonna group this one and this one as AS. Okay, so that is your definition of the scattered wave. Right, and that's it for today. Goodbye.